In this video, we're going to look at constraint optimization some more, and in particular, we're going to look at the introduction. We're going to introduce mathematical programs. So let's look at that and see what happens. All right, the general nonlinear problem formulation is given here as maximize some function of x, where g of x is greater than or equal to 0 and all the x's are non-negative. And again, this is a column vector, an n by 1 column vector, and G is a m by n matrix. For a particular solution, as we've said on a number of occasions, m must equal n, which is preferred. It doesn't necessarily have to be the case, and that implies that the rank of G would be m. Some constraints hold as equalities and they're binding. Other constraints hold as strict inequalities, so they're non-binding constraints and there could be a slack. So we assume that g of x is greater than or equal to 0 and that the x's are non-negative, and that constitutes the feasible set that we're interested in, and a point in it is a feasible point. So any point in the feasible set is a feasible point. So for example, demand cannot exceed supply. So here we have a number of different cases. One is where we find the maximum of this function x at this point x star. So x star is greater than 0 and the first derivative of x star is equal to 0. And you'll notice that if we fall away on either side, so that means that your second derivative has to be less than or equal to 0. Here we have a corner solution where x star is 0, but f prime, the first derivative of x star, is less than 0, so we don't have it equal to 0, and that's where our Karush-Kuhn-Tucker conditions, or KKT conditions, come in. Here is a case where we have exactly the corner solution being identical to the place where x star equals 0, and in that case we get f prime of x is equal to 0. We have this same situation as we have up above here. And then we have an upper bound where x star is greater than 0 at some bound x star. We can't go beyond that. And we find that f prime of x star is greater than 0. In other words, the slope of that function is still increasing as we go. If we were not to constrain this to x star, we would go up here, and somewhere around here we might find a maximum, but that's not possible. So here we have an upper bound on x star. Now, the KKT conditions, we need to modify the Lagrangian method to deal with inequality constraints rather than only equality constraints, and with non-negative variables explicitly rather than ones that can take on any value. So that's, again, we've seen that before, where an important concept in nonlinear programming, because of the nature of the nonlinearity seen in the previous diagrams. So this KKT is important in that case. With LP, solutions are always on a vertex where the first derivative disappears. From the diagrams, the following overall conditions should be satisfied: that the first derivative of the objective function with respect to the x's is less than or equal to 0. The x is greater than 0, greater than or equal to 0, so non-negative, and this condition that x times f prime of x is equal to 0, and this we already saw was the complementary slackness condition. So this is a full specification here of the complementary slackness condition. Traditional consumer demand problem, where we maximize utility as a function of Q1, Q2, P1, Q1 plus P2, Q2 is less than or equal to the budget, and the Q's are positive or non-negative rather, and we usually, when we're doing this, we neglect the KKT conditions in consumer demand theory, but they're really needed because of that second constraint. Another example is where we maximize profit as a function of a bunch of inputs and outputs, which we don't distinguish here, and all of the x's have to be non-negative. In this case, the KKT conditions require that the first derivative of the profit function with respect to any x is less than or equal to 0. Again, the x's are non-negative, and xi or xj multiplied by the first partial derivative of the profit function with xj, they have to be equal to 0. Again, this is the complementary slack, is we've taken these r's and moved it to the left-hand side in order to get this greater than or equal to 0, and that the x's are also greater than or equal to 0. Now, notice that this specification is your general nonlinear or linear programming problem. The KKT conditions are sufficient conditions if f of x is concave and the g's are all convex functions. The KKT conditions are only necessary, in other words, first order conditions, if f of x and all of the constraint functions are continuously differentiable. So you can recall, if you only have equality constraints, you need to examine the bordered Hessian. Now, suppose there are n choice variables and m constraints, then we have this general specification again, and this then is the Lagrangian that is associated with that generalized profit maximizing problem. Okay, so for a minimum, we change these to greater than or equal to and less than or equal to. And again, when you look at any of these conditions, we see that either xj is equal to 0, or this derivative is equal to 0, or both. The fourth interpretation is that for each lambda I in the optimal solution, either the marginal conditions hold as an equality, implying that the constraint is exactly satisfied, or again, that the lambda i's are equal to 0, or both. So again, these are known, 3 and 4 are known as the complementary slackness conditions. How do we interpret shadow prices? Well, if z is the objective function and bj is a right-hand side constraint, then any lambda j is the shadow price, which is given by the effect of a change in the right-hand side constraint bj on the objective function, which is our lambda j. The lambdas are analogous to shadow prices from ordinary linear programming, except that since they are derivatives, they are not generally constant over the ranges of the right-hand side constraints b. That's because you're looking at a continuous function, and what happens is these shadow prices will then be a function of the x's because of the nonlinearity. So if that's the case, then these shadow prices are instantaneous projections of how the objective function will change given an infinitesimally small change in bj, the right-hand side constraint. Special case of linear programming or nonlinear programming, and that's the quadratic programming, where the function f of x is a quadratic, and we denote that in matrix notation like this. So we have a linear component plus the quadratic component here, where this is our function or our matrix of the coefficients. Ax is less than or equal to b, and this quadratic form here occurs. For a maximum, the objective function must be concave. For a minimum, it must be convex. Concave implies that this quadratic form omega is negative definite or negative semi-definite, and for minimum, when it's convex, it implies that the omega is positive definite or positive semi-definite. So we take these results and we convert them to the following. So we've added A1 and A2, where A1 and A2 are artificial variables that are the first to be driven out of the basic feasible solution, which we will discuss in a later set of slides. S is a slack variable as usual, and 4 and 5 are the complementary slack conditions. So these are our complementary slack conditions, as I mentioned earlier. Now these two are very important, okay? These A1 and A2 are from 1' and 1, 2, and they show up here. This arrow isn't quite hitting that point, but it points to A1 and A2. So we try to first drive A1 and A2 out when we're doing the solution, and we'll discuss that a little later on. Lambda S, where S is the slack variable, either S is 0 or lambda is 0. And the same thing here, these are your Kuhn-Tucker conditions. To handle these three, either the lambda or the S has to be in the basic solution, the basic feasible solution, so the other has to be in the non-basic. And the same thing with mu1 or X having to be in the basic feasible with the other in the non-basic, and with respect to mu2 or Y. Only one of each pair can be in the solution at any given time. So in conclusion, we begin by maximizing Z equal minus A1 minus A2. Then we have solved the original QP. Why? Well, the new problem takes into account the optimization as the first order conditions are met already, because we've derived the first order conditions, plus we have shown that the problem to be maximized as what was to be a maximum, the problem is a maximum because this quadratic form was negative definite, which we showed earlier. The advantage of QP is that a QP problem can be respecified as an LP, hence QP problems are treated as separate options in solvers such as GAMS, and in other programs such as Excel, the problem needs to be set up as a linear program as shown by solving for the first order conditions. One of the interesting models is a price endogenous model, where we have that the demand price is equal to alpha minus beta QD, where Q is demand, and that the supply price is A plus B QS, supply function. In equilibrium, the two must equal each other, so that alpha minus beta QD equals A plus B QS, and that QD equals QS, so then we can solve that. It's important to recognize that quantity supplied must be equal to or greater than demand. So supply must always be greater than or equal to demand, but if quantity supplied is greater than quantity demanded, then the price is equal to 0. At least the shadow price is equal to 0, where the shadow price P star is an equilibrium price. So thus, we would require that minus QS plus QD multiplied by this shadow price equals 0, and that's a Kuhn-Tucker condition. All right, so we have that condition has to equal 0, which is this one here, and then the Lagrange multiplier, which in this case is price, is equal to 0. And we can show that here, where supply exceeds demand and the price is effectively 0. To solve for the equilibrium quantity and price, the objective is to maximize the area under the demand curve minus the area under the supply function. That would give us the following quadratic programming problem, where alpha QD minus 1/2 beta QD squared minus A QS minus 1/2 B QS squared. This turns out to be the area, and you can check it for yourself if you like, between the demand and the supply curves, and that's what we want to maximize. QD minus QS has to be less than or equal to 0. In square brackets here, this P is the Lagrange multiplier. We have this non-negativity constraint, and P star is the Lagrange variable or dual variable associated with the first constraint. In the previous figure, we had that it was equal to. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.